When I was working as an engineer before I started teaching, one of the things that we often did was to have to solve problems that were related to motion or velocity of things or energy. But often those things can be interchanged. So in the past, we did an example where we had like a flower pot sitting on a ledge, and let's suppose that ledge is 20 meters high, and my flower pot is 2 kilograms, and I go out and I bump into the flower pot, or I kick the flower pot, or something happens and the flower pot goes flying off and it falls. So we did this when we did kinematics. We actually had a flower pot, not a real flower pot, but we had a problem with a flower pot. And this flower pot, let's suppose that it has an initial velocity, V naught, of 5 meters per second in the horizontal direction. Okay? So it's going off in the horizontal direction. And we know what's going to happen. It's going to follow a parabolic course, and it's going to hit the ground like that, somewhere at some distance away from the ledge. Now, in kinematics, we can solve for things like this dx, dx, like how far away it hits and the angle that it hits and all kind of other stuff. But we can also do some of that work using energy. So let's look at it from the kinematics perspective first. If I want to find out what its vertical velocity is, there's an equation, and it's on page 14, way back when we did kinematics in your journal. So in that equation, we say that VF is equal to the square root of VI squared plus 2AD. So we have VF is equal to the square root of VI squared plus 2AD. And VI, since we're looking at this in the y direction, and in the y direction, there's no falling yet. No falling has occurred. So this part is equal to 0. So we have V final, when it hits the ground in the y direction, is equal to the square root of 2AD. And we can substitute in for A, we can substitute in G right there, because it's gravity that's making it accelerate in the downward direction. So we end up with the square root of 2 times 9.8, I'll just call it 10 meters per second squared, times 20 meters, which is the height of my ledge right there. So that means that Vy at the bottom is equal to the square root of 400, if I multiply all those together, which means it's equal to 20 meters per second. All right? So 20 meters per second is the vertical velocity. But what if I wanted to find the actual resultant velocity that combines the horizontal and the vertical components? Well, we have to go back to Pythagorean theorem, right? And we know that the actual velocity, the actual final velocity squared, is equal to Vx squared plus Vy squared. So that's going to be equal to, in the x direction, we have 5 meters per second. So we have 5 meters per second and all of that squared, plus 20 meters per second and all of that squared. And that's equal to my final velocity squared. So 20 times 20 is 400, and 5 times 5 is 25. So my final velocity squared is equal to 425, and that has units of meters squared per second squared. So I take the square root of both sides. The square root of 425 is not much more than the square root of 400, which is 20. So my final velocity there ends up being something like 20.6 meters per second. That's the final velocity coming in at an angle, the combined velocity both of the x velocity and the y velocity. Okay? So that's kinematics. We did that months ago. So what about energy? For energy, I know that the final energy, this is not going to last the final energy is equal to the initial energy because energy is conserved. And each of those has components. So we have KE final plus PE final is equal to KE initial plus PE initial. When it hits the ground, it has kinetic energy, but it no longer has potential energy because it's on the ground, right? So for potential energy, the final potential energy, that's going to be 0. So I have kinetic energy, final, is equal to kinetic energy initial plus potential energy initial. And I know the equations for those. I have 1/2 mv squared plus mgh. That's kinetic energy, and that's potential energy. So let me substitute in what I know. I know this is 1/2 times 2 kilograms times 5 meters per second. That's the horizontal velocity when I kicked it or knocked it off, and that's squared, plus 2 kilograms times 10 meters per second squared, 9.8 really, times 20 meters. That's my height, m, g, and h. When I solve these, 5 times 5, or 5 squared, is 25, times 2, but also divided by 2. That's 25, and that's kilogram meters per second squared, which is, or kilogram meters squared per second squared, which is a joule. And we have 2 times 10 times 20, that's 400 joules. So the total energy is 425 joules. That's equal to 1/2 mv squared. So I can rearrange this equation. When I rearrange this equation, I end up with v squared is equal to, well, 2 times my energy, my final energy, divided by my mass, which is 2 times 425 joules divided by 2 kilograms. Well, the 2's cancel. That's just convenient. It doesn't always happen that way. So if I take the square root of both sides, I end up with velocity is equal to the square root of 425, which, surprisingly enough, or maybe not surprisingly, is 20.6 meters per second. So these two numbers, these two velocities, are the same. Okay? This way over here, I did it with energy. And truth be told, I really didn't even need the mass. Because, remember, kinetic energy, 1/2 mv squared. I have m here, I have m here, and I have m here. I can factor out the m's, and they actually cancel. So I really don't even need the mass. Okay? I just included it for completeness. But you can see that I end up with the same answer, but I didn't have to go through Pythagorean theorem and all of that. Often there's two different ways to solve a problem. Now there's an advantage to using kinematics. The advantage to using kinematics is that, well, over here, remember I had 20 meters per second. I don't know if you can read that, and 5 meters per second. And I solve for the resultant. Let me replace that with better lines. So there we go. There we go. So the resultant was equal to 20.6 meters per second. This was 20, and this was 5. Those were my x and y, or y and x numbers. With doing it with kinematics, I can separate this out, and I could solve for, say, this angle or this angle if I wanted to. All right? I can't do that with energy because unlike this velocity here, which is a vector quantity, energy is not a vector quantity. It's a scalar quantity. So when I solve for the final velocity, this velocity is in, I can't really determine with the energy equations the direction. Okay? It certainly has a direction, but because it came from this energy equation, which does not have any kind of direction, I can't really assign a direction to it. But if I'm just looking for this velocity, either way gets it. And energy means I don't have to use Pythagorean theorem. Also, I can solve for things like height. Height is one of these in here as well. Okay? And it's over here. If I told you that I dropped something and it fell for 2 seconds, how far did it fall? That would be solving for height. You could do that with kinematics. You can also do that with energy. Okay? So there's lots of things that we can do either way. Okay? There's even other ways that we can solve these kind of problems, but we haven't learned any of those yet. So what you're going to do now is take notes. The notes are moderately long. I don't expect you to take all of the notes. I summarized the kinematic equations that we looked at, and I summarized the energy equations that we looked at, and I also gave you a couple of examples. I want you, when you're taking your notes, to take notes only on the things that either are new or new to you, or things that were that you forgot or that you need to remind yourself about in order to do this kind of problem. Okay? Our worksheet is just this kind of problem. Solve it this way, prove it this other way. Solve this using kinematics, prove that it's the same with energy. Or solve with energy, prove that it's the same with kinematics. The very last problem is a ball, also 2 kilograms like my flower pot. I was lucky I didn't choose a different number, that falls a different height and has a different initial velocity. But it's almost exactly the same problem that I have on the board. That's the last problem on your worksheet. So I would suggest you copy some example either out of the Canvas notes or the one that I did on the board. Take notes only the things that you need to remind yourself about, and then complete the worksheet. Any questions? All right.